All right, it looks like for the most part people have made it into the room, so I'm going to go ahead and get started. I'm Alan Deutsch, and I'm here to tell you guys about esoteric data structures and where to find them. I hope you enjoy. So you might be wondering who I am. I'm a student at DigiPenn Institute of Technology. It's a small school in Redmond. We make video games. I'm studying for a computer science degree, and I've interned as a software engineer at Microsoft Studios' global publishing team and as a program manager within Xbox in the Advanced Technology group. And I'll be returning once I graduate as a full-time employee there. So the first data structure that we're going to talk about is slot map. Slot map is an unordered container, which means that your data, regardless of the order you put it in, may not be in the same order later on. And it's associative, so when you insert something, you're going to get a key to find it later. It stores all of the elements that you've inserted into it in contiguous memory, so there's no gaps, which gives it great performance for iteration. And all of its operations are very consistent. And I'm currently proposing it for standardization through SG14, and it's in Library of Evolution working group now. So the red asterisk is because the committee may change the name. So if you're watching this video in like 5 years and you're thinking, wow, there's something just like this in the standard, but with a totally different name, that's probably why. So the problems being solved by a slot map are that you have some items that need unique identifiers, and you have to have consistent performance. So this is specifically from games. We have a very tight time schedule, and it needs to be consistent for a pleasant user experience. And so making sure that we don't have amortized costs that could spike unexpectedly is desirable. And we also get to reuse memory so that we don't have to do lots of allocations and deallocations. Another nice feature of slot maps is that they avoid ABA-like problems, which is where you have some data that you've put in and you have a key for it, and then later on somewhere else in the code that element gets deleted, something else gets put in with the same key, and then you have the key from before trying to access it. Slot map uses a generation counter mechanic to avoid that problem so that new keys that get handed out will not incorrectly get old data. So it can be found in game engines. It's also very similar to a pool allocator. So if at some point you're a bit confused about what it is, just think of it as a pool allocator with something resembling a map interface. And then in the future, once it's standardized, I expect to see it in browsers, compilers, and more, as those are some of the interest groups that have shown that they're interested in having it. So the guarantees of a slot map are that it has true constant time lookup, erase, and insert operations. So rather than being amortized, these will always be a fixed cost. There's no hashing or anything going on that could change it, with the one exception that insert will be ON when it needs to reallocate and grow. So insert calls will return a unique key to the user, which they can then use to access their data in constant time. And it's a fixed set of operations. There's no hashing or anything. So again, very consistent performance. And the keys to erased values won't work until an overflow occurs. That's on the generation counter, so if it wraps around from whatever your max value is back to 0, then you could have ABA problems. So one of the common alternatives to this is using a hash map, but the lookup costs are inconsistent in those due to both hashing and probing. And the hashing has a high overhead, which is also undesirable. And in many cases, you might not care what the unique key is, just that it's unique. Whereas in a hash map, you have to create your key. A slot map, you don't. It gives it to you. This hash map is also prone to ABA problems, and at least in the STL for us C++ users here, it's not contiguous. So a lot of undesirable characteristics for the types of problems that a slot map solves. Another alternative would be using an array or a vector. You can use the indices kind of like keys, and since it's all packed together, it's going to use a bit less memory than a slot map because it doesn't have some of the overhead to make the guarantees. But the downside is that when you want to remove something from it, that's going to either invalidate everything after it or at least the last element that might need to be shifted into that spot. And arrays are also prone to the ABA problem. So the way that a slot map works is you have an array of data, right? So that's pretty straightforward. You're going to keep all of your elements stored there, and as you can see, they're packed towards the front in contiguous memory. And where the real magic happens is in a slots array. So that's this guy. It'll have these two values in each slot, and one of them is an index, and that index will go into the data array. and the other value is a generation counter, and that's how we solve the ABA problem. So as you can see, all of these indices correspond to some data that's being stored. It also uses a free list mechanism in order to have O1 inserts. That way it's able to find a free slot in constant time. And you'll note that the free list head has an index in it. That index is set to the next element in the free list, so it's able to store it all in place. So the way that insert works is we have some element that we want to insert that'll go in the next empty slot available. And so we're going to put our data there, and then moving forward, we have to pop something off the free list head. That's going to be the slot that corresponds to our newly inserted data. And we generate a key that points to that slot. We have to match the generation to make sure that when we look later, we'll not have those ABA issues. And then we update it to point to our data, and we can then return our key to the user. And the key will point to the slot, not the data itself. So there is that layer of indirection there. To erase something, you give a key to the slot map, and it'll have an index and a generation. So the first thing we're going to do is check the generation. In our case here, the generations match, and so we can go ahead and proceed. So we're going to increment the generation to make sure that we don't have any issues with ABA going forward right off the bat. Then we can find the element that it's pointing to and go ahead and destruct it. And then once that's destructed, we're going to move the last element into its slot. Then we need to find the entry in the slots table that corresponds to that and update it to point at the new address that the moved element is in. Then we need to go to our free list tail, and what we're going to do is add the newly vacated slot entry and set the index of both of them to point at the vacated slot. So what this does is it adds it to the free list, and the last element will point to itself so that it can detect that it's at the end. Finally, we set the free list tail to point to that newly freed slot, and we're done. So some of the trade-offs of a slot map are that the dynamic sizing can cause memory usage spikes. Especially in games, this can be a problem where you have space for 1,000 elements, and then you want to go and grow it. And typically that's going to be a 1.5x or 2x growth. And so you not only need the memory from before, but also the new memory, which is a big jump. Whereas something like a hash map that's node-based, you wouldn't have this sort of issue since you can allocate just the node you need. So at those times it can spike in memory usage, but it's otherwise quite consistent. Also, due to the dense storage, the addresses of the elements are unstable, so the lookups are a bit slower than just using a raw pointer. It also uses additional memory to make some of its performance guarantees, which may be undesirable in some circumstances. So one of the common variations is not using the index table. You're able to save a bit of memory by that and have stable indices and pointers. The way that it works is you just store the slot data right next to the data itself. And so by doing that, you don't have the indirection in memory either. So it trades faster lookup times for worse iteration performance. And also it has the downside that the elements aren't densely stored, which is what causes the worst iteration performance. Another variation is using a fixed size array. So this one will have constant time insert in all cases since it doesn't ever grow and crashing is constant time. But the generations increase roughly uniformly as well since they're all allocated from the start and there's no memory usage spikes. Unfortunately, dynamic sizing is typically something that we want to have, and so this variation isn't usually what we'd want. And some of the edge cases can cause the generation to overflow quickly. Another one is using block allocations similar to a deck. So that one also has the O1 insertion, and the allocation memory usage spikes are a bit smaller than using a vector-like backing. And the iteration performance can be tuned to get pretty close to just having a fixed single block of memory. But the elements aren't stored fully contiguously because of the gaps in memory, and the cache misses scale inversely with the block size, so the smaller your jumps in memory usage, the worse the cache performance is. And the lookup has an additional indirection since it also has to find the correct block. So the way that it works is the keys are some sort of decomposable pair of integers, at least in the current state of the proposal. So the first is the index and the second is the generation. And the index from the index array is used when the generation counters have been detected to match, and then the keys can be tuned a bit by the user as a specified template parameter. So the next data structure that we're going to talk about today is a Bloom filter. Bloom filters are a really interesting hashing-based structure. They use up a fixed amount of memory, and rather than hashing the element and storing both the element and some sort of key that's used to find it using a hash, it's a probabilistic data structure, which means that it doesn't always guarantee correctness, but it uses a lot less memory and gets pretty close. And you can tune your error percentage with these. So the probabilistic part is that sometimes it'll say an element is in the set when it really isn't, but it doesn't actually contain any of the elements, it's just a bunch of bits. So it only supports find and insert operations, you can't remove things from it, and the only options that you can get from a find are that it's definitely not there, or if it says that it is there, it could be incorrect and the data's actually not, and so that's where the probabilistic part comes in. So the problem being solved is typically when you want to check a set for the membership of an element. So you have some data and you want to see if it's in your set. And Bloom filters are very efficient with memory. They use far less than any sort of set representation you would have that actually stores the elements. It's like several orders of magnitude better. And the trade-off here is that you have to be okay with it probably being right and not always being able to guarantee that it's correct. So the guarantees that it does make are that it'll have constant time for both insert and lookup operations, and its memory usage is constant, and none of the actual elements are stored. And that's kind of an interesting property, that the elements aren't stored, because it means they can't be reconstructed, and it's privacy friendly. So if you want to keep track of some user data without actually having the user data, this is a cool way to do it. So the most common alternative would be something like a hash set, where there's only one hash per lookup, which is typically going to be better than a Bloom filter, but it's going to use more memory since it has to store all of the elements, and they're generally not contiguous since they're typically implemented as a red-black tree. And it also contains the elements themselves in a hash set, which in some cases could be quite desirable, in others it might not, such as the privacy cases. So the places you can find a Bloom filter are in things like website safety, email contacts lists, newsfeed pruning, type-ahead search for looking for your friends on like Facebook, and even as an early out for expensive queries. So the way that some of these work is that, say for example with the early out example, you would have a Bloom filter representing your files that you have on disk, perhaps, and before doing the expensive file I/O operation to read from disk, what you can do is query the Bloom filter to see if the element is there. And if it says no, you can be 100% certain that the element really isn't on disk. And if it says yes, there's a pretty good chance that it is there, and then you can go ahead and take that more expensive file I/O operation. So the way that a Bloom filter works under the hood, let's start with the storage. It's actually a bit array, and as I've said before, it doesn't have the actual elements. So that looks something like this. We have our bits 0 through 23 for a total of 24 bits. And these are going to get set by various hash functions whenever you insert an element. And the way the hashing works is that you'll have k hash functions, and k is some user specified amount based on the margin of error you want. And then each hash will set one bit based on whatever element you're inserting. And so for these, you prefer speed over security for your hash functions. Since you're not storing your data anyway, it's not that important that they be cryptographically secure. So the hashing, we have our two nice little hash functions here too. I chose to give them cute names like FNV1A and Murmur3. So to insert something, say auto, it goes through those hash functions and you get some sort of value out. And then you find the bits that correspond to those values, so at those indexes, and you go ahead and set them to 1. And so I have this little set on the right side here. It's not a real set, but we're just going to keep it there to keep track of the elements we've added for later. So let's add a couple more elements. We can put in a struct as a string, template, class, and constexpr. And so the way that lookups work is that they're similar to insert. You also take it and run it through the hash functions, but rather than setting bits, you check that the bits are set. So let's say we want to look up constexpr, which is one that's in there. We get our bits and we check them, and both of them were set to 1, so they're found. And that means that it's probably in the Bloom filter. It was probably inserted at some time, but again, we're not 100% sure, but in this case, it happens to be true. Another one would be var. So we can look that up and we get a couple of bits, and we check them, and one of them's set, but the other is set to 0. So we know for sure that that element's not in there, because if it had been inserted, both of those bits would have been set to 1. So another example is hello. And so this one will point to a couple of bits that were both set to 1, but as you can see in our little example set on the right, it was never actually inserted. So this is the case where you have to watch out for and be okay with if you're going to use a Bloom filter, because it can be incorrect at times. So that's where the probabilistic part comes in. The false positives can happen, but false negatives don't. And the amount of these can be tuned. So let's look at how that works. If we have a number of hash functions k, then we can set that based on the negative log 2 of p, where p is the desired false probability rate. The other thing that you might want to tune is the number of bits, or otherwise the memory footprint of your Bloom filter. So in this case, m will represent the number of bits, n is the number of elements inserted, and p is, again, your desired false probability rate. So that's the equation for figuring out how many bits you want. As a small disclosure, I'm not really a math guy, and I just kind of took the math from Wikipedia, but it's probably right. So the takeaways from a Bloom filter are that if you're willing to accept some error, you can save a lot of memory. It's also able to store data without actually storing the data, which is a kind of cool way to think of a data structure, and not something I've seen in many other places. So the next adventure we want to go on is navigation meshes. And it's a bit of an adventure because they represent how you find things. They work well with A-star search algorithms as a representation of the search space. So a navigation mesh is a graph, and it works for 2D or 3D. And in general, it'll produce fewer nodes than other representations of a 2 or 3-dimensional traversable search space. So the problem being solved is that you have some search space you want to represent, and you need to know which areas of it can be traversed and which can't, and probably want to pathfind around it, typically in like a game or something. So some of the other representations we might have for this are a grid, right? We can look at a grid with some example map here, and you can see that there's a lot of nodes, and also the edges are quite jagged. So it doesn't really smoothly fit the walls. And so if we want to pathfind from that little nook in the bottom left on the right side of the map to the nook in the bottom right corner on the left side of the map, like so, the path takes 17 nodes, and there's 370 total nodes required to represent this map. So that's not great, and we can probably do a little bit better. So if we look at a hex grid representation, there's also a lot of nodes, and it doesn't handle the walls and corners very well. But at least this one, it has equidistant nodes. So even if you're moving diagonally or whatever, the cost for moving from one node to the next is equal. But it also has some issues with not perfectly representing the search space. So if we run that same search again, we can find that 9 nodes are used, which is a lot better than before. And 85 total nodes is also quite a bit better. But I still think that we can do better. So let's look at what a nav mesh can do. This is a triangle-based nav mesh, so all of the nodes in this graph are triangles. And as you can see, it uses a lot less nodes than any of the previous representations. It smoothly handles the walls and corners, and it's a pretty tight representation of the search space. But there are some oddities, like those little skewed triangles that are really thin and don't do a lot. So our path this time is 7 nodes, which is only a couple less than before, but that's also one of the worst cases for this particular map's triangle representation. And the 16 total nodes is a lot better, so in your worst case search, you're going to come out a lot further ahead than you would have otherwise. Finally, we can look at a triangle and quad-based nav mesh representation. So in this, there's very few nodes. The walls and corners are all smoothly handled. It's got a pretty clean layout. It tightly represents the search space, and as an added bonus, all of that expensive triangle math is mostly avoided with just one triangle on this representation. So our search example here, we only have to cross 3 nodes to get from start to finish. That's a huge improvement from our start. as well as the 9 total nodes. So for this particular example, it was 1 order of magnitude better for the search from the original grid representation, and 2 orders of magnitude better for the total search space representation. So that's a big improvement. So the big takeaways from a navigation mesh are that it represents the data in the way that it exists better. And so that's something that we can keep in mind as we build solutions to our own problems. Just because there might be a common representation for similar problems doesn't necessarily mean it's the best way to do it. And in this case, we're able to make each node store a lot more data. Rather than having to have each individual grid cell connected with all those edges, we're able to make much larger ones that cover a big swath of area that's easily traversable with no obstacles between it. I'd also like to talk about hash pointers. These are another really cool data structure. So they're, from the name you might have guessed, a pointer. But what they also do is store a hash of what they're pointing at. And so because of this, you're able to verify the data is the same state that it was in when you first put it there or got your pointer to it, and it's pretty tamper resistant. The problem being solved by a hash pointer is that you need to locate your data and you want to verify that it hasn't been changed since you got your pointer to it. So this is a really useful tool, and it's found in a few places, mainly in blockchain and Merkle trees, which are the 2 data structures that are derived from it. And both of those are common in cryptocurrency, which has become quite popular these days. The way that it works is you'll have the pointer to the data and the hash of the data. As you can see in this example here, pretty straightforward. So for a blockchain, one of the first derivatives, we have the hash pointer as well as some data that makes up that block. And each of these blocks has a hash pointer to the previous block. And so using this technique, you can make something like a secure log or cryptocurrency, which logs the transactions. So the way that tamper detection works is, say you have some case where a black hat wants money and they want to go alter the blockchain to give themselves more money in a transaction that never actually happened. And so, ideally they would just go in and change history to add that transaction, and all of a sudden they're really rich. Sounds great, right? Not for everybody else. So the way that we can figure out how this is solved is actually just diving in and seeing what it looks like if someone were to try to modify a value in a blockchain. So the first thing that we're going to do is assume that this data has been modified in some way. So we're going to represent that with red. So seems straightforward. In any other data structure, this would probably be a problem, but not with blockchains and hash pointers. The hash for the next block has now been invalidated since the data has changed. And so that means that we can detect that the data was tampered with. So that works, and it only took 1 block to do so. But let's say we have a really, really persistent hacker here, and they want to tamper with the hash too. So let's see what happens when they do that. They go in and they tamper with the hash, and now our hash pointer is valid again. But oh wait, it's all better, right? They've got their money, but not so fast. There's the hash of the next block. And so that one has now been invalidated because those hash pointers are stored within the blocks themselves. And so the hash for the next item down the chain includes the hash for the previous one. So in order to fix this, they'd have to change the next hash as well. So let's say they do that, and they run into the same problem again with the newest item on the blockchain. Again, the hash has been invalid, and it will no longer be an accurate representation of the previous block. So with blockchains, tampering is really hard, and every downstream block must be modified in order to have a successful attack. The downside of this is that detecting these attacks is an ON operation. You have to go through all of the entries in the blockchain after it in order to detect it correctly. So there's another approach, which is a Merkle tree. This is a tree-based data structure made by Ralph Merkle that also is based on hash pointers. And in this one, only the leaves hold data. All of the nodes up the tree simply contain hash pointers. So this is roughly what a Merkle tree would look like. At the top, you have a couple of hash pointers for the left and right side, and then each of those will also have hash pointers. And then down at the bottom, you have just the data. And so to detect tampers in a Merkle tree, you have to traverse to the element from the start of the tree, which is O log n, since it's a tree. So that's a bit better as far as tamper detection goes, and it's easier to detect that your data has been modified. But if you're a hacker and you want to go in and modify the data and not get caught, you only have to modify the things up the tree from whatever you're attacking, rather than having to modify every single block in the chain. So the takeaways from a hash pointer are that tamper detection gets really easy if you use them, because now a hacker has to do all of this work changing all of the data all over this structure, whereas you just have to follow it and see that all of the hashes work still. It also means that the hashes can be used for more than just finding data, but you can actually use them to make sure your data is unchanged as well. And so this can have practical applications in all sorts of other domains as well. So that concludes the containers that I'm here to talk to you about. So if you have questions or comments, please step up to the mics. Yes. Thank you. Mm-hmm. Can you step up to a mic so they get it on the video? Thanks.
Hi. So about the navigation mesh, can you please explain a bit more about when it's useful and how it works? Because
yeah, so it's a graph representation, just like a grid would be or any other graph that you might be used to with nodes and edges. And it's used typically in games for 2-dimensional and 3-dimensional search space representation for pathfinding problems. So you have a character that wants to go from point A to point B, and there's only certain areas of the map that they can walk on, and those areas are connected in some ways. The navigation mesh represents those, and you're going to typically use an A-star search to get from point A to point B.
Okay. Okay. I don't really understand the actual implementation though, like the other data structures you mentioned. So it's.
What specifically do you mean?
Never mind. Talk to you. I think
okay.
It's too much.
Yeah, you're welcome. We can talk after.
So for the bloom filters, is there a concept of delete? And if so, how does that work?
No, bloom filters don't support delete, but there are some other derived types of data structures that use a similar technique, and some of them do.
Okay. Cool. And do they just keep another structure on top of that?
Yeah, typically they're going to use more memory, and that's how they're able to do it. Like, for example, a count min sketch will have multiple arrays of the bits rather than just a single one, and each hash gets its own array.
Okay. Cool. Thank you.
Yep.
Is there a well-known algorithm for the navigation mesh for decomposing the unblocked polygon into rectangles and triangles that produces the graph?
Yeah, so the most commonly used approach is through a software package called Recast. It's open source, available on GitHub. It's used by both Unity and Unreal engines. And so typically anyone going with a navigation mesh would use that. I don't know all of the details of how the nav meshes are constructed by it, but I know one approach is something like a flood fill. You're welcome.
This is just a comment about hash pointers. Possibly a more commonly known example is Git revisions.
Sorry, what?
Git revisions.
Oh, Git revisions, yes.
Git revisions are in themselves. Each Git revision is a hash of its entire log all the way back to the very initial commit that created the repository. So it's pretty much on the same idea.
Yeah.
So on the navigation map, it seems that your area just gets bigger and bigger, so you don't really have much detail on the path. I mean, what I don't understand in terms of the trade-offs on knowing what kind of path, how much path do you need to know?
So the way that the navigation mesh works is each node will only represent traversable terrain. And so you don't actually have to represent terrain that can't be traversed because there simply won't be a node for it.
Okay. So it's all a matter of the application, how much area in each node.
Correct, yeah. And then you just go between the edges of the nodes to find where you can go from your current position.
Okay, thanks.
Yep. Looks like there's no more questions. Thank you all for coming.